Hello everyone, my name is Hieu. I'm from Pukyong National University, Department of Ocean Engineering. And the title of my study is System Identification for Layer Half-Space Problem by Unscented Kalman filter. Firstly, I would like to introduce some basic concept of system identification. System identification shows inverse analysis to extract the true physical parameters based on the indirect measurement. For example, we have a structure with some unknowns and we cannot directly measure the unknowns. We use some sensor and some signal recorded by the sensors. We use the inverse analysis to identify the unknowns. This process is called system identification. The inverse analysis can be divided into deterministic or probabilistic method. For deterministic, we need to minimize an objective function. This objective function is to quantify the difference between the calculated responses and the measurement. And for the probabilistic method, we use the Bayes theorem, in which the posterior distribution is proportional to the likelihood and the prior distribution. I will introduce some basic algorithm of the probabilistic method. The first one is a Monte Carlo simulation. In this method, we generate many sampling points, which is generated from the unknowns, and we use this sampling points to calculate some sampling measurement. And the disadvantage of this method is calculation time. Another method, which is extended Kalman filter. In this method, we don't need to calculate. We don't need to generate many sampling points. We need the Jacobian matrix to update and predict the unknowns and its covariant matrix. The disadvantages of this method is the accuracy and the difficult to find the Jacobian matrix. The last method is the Unscented Kalman filter. In this method, we use some sigma bonds, which is symmetrically and elliptically generated, so that the mean of the sigma bonds is a current state, and with the sigma bonds we will calculate some sigma observation, and finally we can update and predict the state and the covariance of the state based on the sigma observation and the sigma bonds. The advantage of this method is the accuracy, and it's easy to implement and in this study we will use Unscented Kalman filter for the system identification problem. The problem we considered is the layer half-space problem. We will use the Unscented Kalman filter to predict the material property of the soil based on some measurement at the surface. And the next one, I will go detail on the algorithm of the UCAF Unscented Kalman filter. Firstly, I will propose some definition. The covariant matrix of the state is termed as P. Covariance of the measurement is R. Covariance of the process is Q. At time k-1, we define the state theta, which consists of the unknown the parameter to be estimated. And from time k-1 to time k, we can we can propagate the state by this transition function, In this equation, W is a Gaussian noise, and at time k, we can also find the measurement from the state by this function, and in this function, the V is a Gaussian noise also. For the UKF algorithm, we use the sigma bond to capture the mean and the covariance of the state. The UKF algorithm use the sigma bonds to predict the state and its covariance matrix. Sigma bonds are set so that the sigma bonds can approximate the distribution of the state, and these bonds are chosen in a specific way to capture the mean and the covariance of the distribution. Sigma bond will be symmetrically and elliptically distributed around the mean, which is theta. And corresponding to each sigma bond, we can generate a observation, and also corresponding to a sigma bond, we have a weighting factor. The weighting factors here are used to determine how much influence of the sigma bond should have on the resulting mean and covariance estimate. For example, if the sigma bonds that are more tightly clustered around the mean will typically have higher weighting factor, and if the sigma bonds are far away from the mean, the weighting factor will be small. We use the sigma bonds and the observation from sigma bond to calculate the Kalman gain, which is the most important matrix of the UKF algorithm. The detail of the UKF algorithm is shown here. The first step is initialization. We initialize the value of the rest state and its covariance matrix. Then we predict the state and the covariance of the state, and then we generate the sigma bond, calculate the measurement from the sigma bonds. We calculate the covariance matrix of the response and the cross covariance matrix of the state and the response. Then we move to the update step. We will calculate the Kalman gain based on this matrix, covariance of the response and covariance of the state, cross covariance of the state and the response. We calculate the Kalman gain, we obtain the Kalman gain, then we have a matrix to tell us how much we should modify the state. If the Kalman gain is high, it indicates that the measured state is more reliable and should be given more weight in the final estimate. And on the other hand, if we have a low value of Kalman gain, it indicates that the predicted state estimate is more reliable and should be given more weight. The next is a thin layer method. We use thin layer method to obtain the response of the layer half space problem, and for this method, the layer half space is divided into some thin layers, and we have the covariance equation related to some matrix from finite ensemble of the problem. And in this equation, U and P is a complex response, displacement response, and complex harmonic excitation. This equation can be solved by eigenvalue problem, and then we can have the displacement response subjected to the harmonic vertical slope at the surface in time domain. and basic equations. And solution of thin layer method is analytic in horizontal direction because we do not um, discretize the problem the mesh size in the horizontal direction. We only discretize in the vertical direction, so the solution in the horizontal direction is exact, and the accuracy and efficiency of thin layer method is dominant. The other methods such as finite element or finite difference methods. To apply the UKF to the problem inverse alpha problem, we will estimate the shear wave velocity, and we define the state like that. Mm, and we use a time history response of the surface to as an observation by the equation I introduced before. And for this problem, we need to add the regularization to improve the accuracy. The regularization is added so that we assume the zero difference between the material properties of the two consecutive layers, and corresponding to this accruement measurement, we have the accruement covariance matrix R as follows. Next is the application. Firstly, we will apply to various layer half space profiles, and the properties of the investigated problem are shown in this table, with some location of the measurement and frequency of excitation here, and the value of initial gas for covariance matrix of the state, and the covariance matrix of the process also introduced. To um, to to compare the accuracy of the problem, we use a relative error, and the equation for relative error is shown here. Here is a result. We use initial gas around 280 meter per second as initial value for the beginning of the algorithm. Then we can have the very accurate result, and we can also obtain the standard deviation or the distribution of the estimated profile compared with other methods from gradient based or genetic algorithms. In the previous study, we can see that the UKF algorithm can return some acceptable and competitive accuracy. The next problem is a payment system. For this problem, we have the very stiff layer as a surface, and in this problem we consider the noise to investigate to check that is it possible to apply the algorithm to more complex problem. And here is a result. In this figure, it shows that the UKF algorithm can predict the good prediction for the complex problem. For the more complex problem, even if we consider the noise and compare with other method, we can see that the UKF algorithm can have the good result, can improve the result a little bit. And the final problem we consider is the application of UKF to the real world cell physical data, which have very irregular layers. And for this problem, we also consider the noise also. Here is a result. Mm, and now for this case, as you can see, the UKF algorithm can predict the result with a very excellent accuracy. And finally, we will conclude from this study. Firstly, the accuracy of UKF is proven for various problems, and in some cases, the UKF algorithm is better than the other algorithm. In some cases, it is not better. But however, by using the UKF, we can update, we can have some posterior distribution for the uncertainties of the estimated parameter, and this posterior distribution can be useful, can be used in further probabilistic analysis such as soil interaction or seismic hazard. And this is all of my study. Thank you for listening.